All right, so we are going to keep talking about how to sketch a curve, and we're going to add another level of it today. So today we're going to look at the second derivative and what it can do for us. So far we've talked about the concept of increasing and decreasing, right? So we have increasing and decreasing. And we know that different parts of the graph can do that. So today we're going to look at concavity. So concavity is being concave, right? And we've got two types. We've got concave up and we've got concave down. Concave up is anything that's round, like a bowl. Concave down is, well, down. So anything that's like a mountain. All right, so concave up and concave down. We can have increasing concavity and decreasing concavity. So let's look at increasing. We know that increasing is when something's going up. So if we're going to have concave, increasing concave up, it would look like this, right? See how this is concave up and it's increasing? And we can do that with concave down too. So this is down, concave down, but it is increasing. So you can have both types within an increasing interval. For a decreasing part of the curve, we know that's headed in a downward direction, and that can have different concavity as well. So we can be concave down and decreasing. So this is decreasing and it has concavity down, concave down, and then we can have the same decreasing but concave up. So this is still decreasing, but it's concave up. So they can both exist, and we're going to start looking really carefully at the concavity within our different intervals. Okay, so let's see what this looks like on a graph. So let's say here's my graph, and I'm going to draw a curve, and this is going to be my curve. Okay, so here's my curve. Now, we've been focusing on where our increasing and decreasing intervals are. And if we look at that, we know that we're increasing and decreasing, and those spots change right about here, right? Like I would say that this is a place, this is an increasing interval, this is a decreasing interval, and this is an increasing interval. But now we want to look at where the concavity changes. So if we go really carefully along here, I'm going to start here. This is concave down, right? And it's increasing. And now we switch to decreasing, but aren't we still concave down? We are. But where does our bowl start filling? Well, it kind of starts filling right about here. And I change to concave up. And this still, even though I've switched to increasing, I'm still concave up. So you can see that the increasing and decreasing is completely separate from where our concavity changed. So the place where concavity changes is called the inflection point. The inflection point. It's where concavity changes. Where concavity changes. All right, that's our inflection point. It tells me where I switch from concave up to concave down. It's going to not happen as often as your intervals from increasing and decreasing. So this is important. The other piece is your increasing and decreasing intervals, They occur when your derivative equals 0. Your inflection points happen, can you guess? When your second derivative equals 0. All right? So all of a sudden our second derivative has a lot of value. It's going to tell us about concavity. The other piece of this puzzle is that concave up exists. Let me write this down. Concave up. Concave up exists when your second derivative is positive, and concave down, as you might have guessed, exists when your second derivative has a negative value. So let's back this train up just a little bit. Let's be really clear. Our original function, f of x, when we set that equal to 0, we find x-intercepts. You've known that since you were in 10th grade. When we take our first derivative and set that equal to 0, that's when we find our min and our max, which is a change of direction, right? Change of direction. Like when we go from increasing to decreasing, right? Increasing to decreasing. And now we know that our second derivative, when that's equal to 0, that tells us about concavity. Concavity. And that is a change in opening up or down. So this is called an inflection point. An inflection point. So this is a good thing to write down. All three levels, if you will, of this function play an important role. So let's see what this legitimately looks like as a problem. Okay. Let's start with a real nice one. Let's start with f of x equals x cubed. Okay, so we know that this is a cubic function. It's a parent function. We know what this thing looks like. It does this, right? So this is where we've got so let's start by just finding our first and second derivative. So my first derivative is going to be 3x squared, and my second derivative is going to be 6x. Okay, so if I set these all equal to 0, I can find important things. So if I say x cubed equals 0, then x equals 0. So this is going to be my x-intercept at 0. Ding, 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 ding. There it is. If I set this equal to 0, I get 3x squared equals 0. The square root of 0, 0, 0 again. Okay, so this is saying that I potentially have a max or a min there. We're going to see. And then my second derivative says 6x equals 0. So again, x equals 0. So this is potentially an inflection point. So I would set up my sign chart here, and I'd put 0 in the middle. Now I'm going to pick some test points on either side. I'm going to pick -1 and +1, and I'm going to plug those in to my derivatives, right? So let's start with our first derivative. So if we start with f prime of -1, we're using the first derivative to check for increasing or decreasing. And I get -1 squared is 1 times 3. So I get something positive. So I'm going to find out that this is positive on that side. And then I'm going to do the other side. 1 squared is 1 times 3 is positive again. So f prime of 1 is also positive. So this is telling me that I don't actually change direction. I'm increasing and increasing. And is that exactly what happens? Yes, this is increasing and this is increasing, so that makes sense. Now we're going to use our second derivative, and we're going to say f double prime of -1. Now 6, I'm going to plug it into my second derivative. 6 times -1 is negative, which means this is going to be concave down on that side of 0. And when I do the same test point, or when I do the same thing for my test point over here, f double prime of 1, 6 times 1 is positive, which means this is going to be concave up. And if I come up here and look at this, sure enough, isn't this concave down on the left side of 0? And this is concave up. So I have increasing and concave down, and I have increasing and concave up. That means that this spot right in the middle is an inflection point because my concavity changed. Therefore, it is a critical point. So this is another type of critical point. All right, so do you see how that's valid and how that works? Let's try another one. Okay, let's try this. So let's say we have f of x equals 2/3 x cubed minus 2x squared minus 16x. So are you getting the vibe already that finding the x-intercept is like next to impossible? And that's typically how we would graph things. And if we can't find our x-intercepts because it's inefficient and annoying, then we need a better plan. So let's find our derivative here. So the derivative here is going to be 2x squared minus 4x minus 16. And my second derivative is going to be 4x minus 4. All right, now this original function would lead me to my x-intercepts if I felt like solving it, but no. So let's go to this guy. What if we can find maxes and mins here, right? This is going to lead me to max and mins. So let's try and solve that. Let's factor out a 2, and then we're left with x squared minus 2x minus 8. And from there, I can factor that, right? So 2 x minus 4 times x plus 2. So that means that we've got x equals 4 and x equals -2. Okay, so this is going to be our max and min. Now let's come over here and solve this guy. All right, so we're going to set him equal to 0 too. So 4x minus 4 equals 0, 4x equals 4, x equals 1. So this is going to be an inflection point, and these are going to be max and mins. All right, now we need to set up our sign chart. So I'm going to make this a little bit smaller so we give ourselves some more room. So let's set up our sign chart, and we're going to focus on these numbers. So we've got a -2 that's a player in the game, a 1, and a 4. But we need to really be careful so we don't mess this up. Like this 1 is our inflection point, and the -2 and the 4 are the increasing and decreasing intervals. So you got to kind of make sure you choose the right one. All right, so on either side of the 1, let's start on either side of the 1. So the test points we're going to choose are going to be maybe 0 and 2, and I'm going to plug those in to my second derivative. So I'm going to plug my 0 in here. So that's 4 times 0 is 0 minus 4 is negative. So that means this whole side is negative, and it's going to be concave down because I got negative, so it's concave down. I'm going to plug my 2 in now. I'm going to plug this 2 in, and 4 times 2 is 8 minus 4, that's positive. So this entire side is positive, and it's going to be concave up. Okay, so that's good. Now we're going to do the same process, but with our increasing and decreasing intervals. I'm going to come over here, and I'm going to erase these numbers and pick new numbers. So we need to pick something over here. Let's pick -3 in the middle. We can pick 1, that's fine. And then I guess we'll pick 5. So if we plug -3 into our first derivative, so -3 squared is 9, 18, -3 is going to be plus 12. So 18 plus 12 is a big number, minus 16. So we're going to get positive. So that means that this whole piece is positive, and this is going to be increasing, right? Okay, now let's test the 1. So if I test this 1, I'm put that in my first derivative. So 1, 2 minus 4 is -2. That's going to be negative. So this whole area here is going to be negative. So this is going to be decreasing. And then let's test our 5. So that's going to go back in our first derivative. So 25 times 2 is 50 minus 20 is 30. Okay, so we're going to get positive again. So this whole area is going to be positive. So positive is increasing. So you can see where this like overlap's happening. So if we want to go graph this thing, what's it going to look like? We're going to be increasing to -2. Let's find -2 on our graph. 1 on our graph. 1 and 4. So we're going to be increasing and concave down all the way to -2 in some way, shape, or form. So we're going to be increasing and concave down. Then I need to stay concave down but start decreasing until 1. So concave down, decreasing to 1. At 1, I'm going to keep decreasing, but I need to flip to concave up. So I'm going to start drawing my bowl going upward. Do you see how I switched here? I made that flip. And then at 4, I'm going to start increasing and stay concave up. So I'm going to do something like this. Now, so this is the shape of the graph, right? This is great. Now, here's the kicker. We don't actually know where these points are right now. Like, how high is this? Is this vertex, this maximum, like here? Is it here? Is this whole thing could be shifted down? We don't know that part yet. We can find that part. We can take our max and mins and stick them back in the original function and find these coordinates. We can do that. We're not going to do that right now because I think you can figure that out on your own. But do you see how our sign chart led us to sketch out the shape of this graph? That was our goal for today. All right, so as a quick review, let's run through this one more time. The original function gives you x-intercepts. The first derivative gives you increasing and decreasing. The second derivative gives you up and down for concavity. All of them have y coordinates from the original function. Okay? So, if you're asked for the coordinate, the y has to come from the original. Has to. You only get the x from the derivatives. Does everybody get that? I sure hope so. Remember, you can be increasing concave down, increasing concave up, decreasing concave down, or decreasing concave up. Lots of options. They mix and match. Make yourself a sign chart, pick some test points, and we're off to the races.